All right. Okay, so last page on the P3 notes. Even functions. Symmetry about the y-axis, an easy function that we know about is y equals x squared. We know y equals x squared looks like this. We know just by looking at it that there is symmetry about the y-axis. But there's also this test that we did, but I just want to kind of talk about this form. And symmetry about the y-axis, we also call it an even function. So even function, easy way to tell if it's an even function for the most part is if all your exponents are even, then that's a good indication that chances are it's going to be an even function, that there will be a symmetry about the x-axis, sorry, about the y-axis. But we want to ensure that there is that symmetry by going through this test. So when we go through that test, you see that my exponent is even there. So there's a chance that this could be a even function. So we go through our test. We say f of negative x. We want to find f of negative x. So f of negative x just means I'm going to take my expression, replace every x with negative x, and see what that comes out to be. Okay. We see that it cleans up to just be x squared minus 5. So we know it passes the test if f of negative x ends up looking exactly like the original function. And it does, right? Here's my f of negative x, here's my f of x. No changes even after I made that substitution. So therefore, our function is even. An easy odd function or symmetry about the origin is y equals x cubed. And here's a visual. All right, we know that an odd function exists visually if you can flip the graph upside down and you can convince yourself you're still staring at the same graph. So typically we call it an odd function because typically if all your degrees are odd, then you have that chance of there being a symmetry about the origin. So here's our test. We start the process the same way. We're still going to replace every x with negative x, but whatever that expression ends up looking like, we're going to match it with a negative version of the original function. We can get those two expressions to match up, then we know that there's symmetry about the origin. So let's build f of negative x first. So that means I'm going to take every x on the right side and replace it with a negative x. The first term, negative x, will stay negative x. This negative x cubed will stay negative x cubed, but there's a negative and negative, so that gives me a positive. So that's going to change sign overall to be plus 2x cubed. So we have f of negative x squared away. Now we want to find the negative version of f of x. So negative f of x just means I'm just going to put a negative in front of my original function. So let's clean this up here. If I distribute the negative through, let's see what this boils down to be. And let's see if we can convince ourselves whether these are the same or different. If they're the same, it passes the test. We know it's an odd function. If it doesn't, if they're not the same, then at least we can say it's not an odd function. So I'll distribute the negative through. Changes the signs of both the terms. And we compare. We see that they are in agreement. F of negative x does match negative f of x. Therefore, we know it's an odd function. Okay, questions? Okay, let's talk about piecewise functions. So piecewise functions are just functions where we're only graphing a portion, right? Only graphing a portion of it. And we're going to take both these graphs, we're going to place them onto the same coordinate plane, but we're only graphing a part of it. The x is less than 1, the x is greater than 1. That's going to end up cutting off parts of the graph, so it's only going to show a piece of each across different intervals. Okay. So the way that we're going to go about doing this, I think the easiest way is we're going to build our table of values using the domain restrictions that's given in our problem. So let me start with y equals 1 minus x. And I want to create a table of values that's associated with this function. I know I want values less than 1. Okay, but here are something that we got to be careful about. I think a lot of students, they see this and they want to start at 0 because it just feels natural, right? Less than 1, let's start at 0 and we'll move our way down. But if you start at 0, you're missing out on that portion of the graph between 0 and 1. Okay, so what we need to do is we're actually going to start at 1, but to ensure that we don't include 1, we'll put an open circle at 1. So think of this as a boundary. The graph is going to go all the way up to as close to 1 as possible, but to ensure that we don't include 1, we'll do an open circle. But we still need to know where that we still need to know where that boundary is for our graph. So we do need to start at 1. Okay. Even though it's less than 1, that less than 1 just means we'll put an open circle there. But we still need to know, we need to have that point actually on our graph. Okay. Now we'll choose values less than 1. Now we can start at 1 and move our way down. So we'll just pick a couple of values, 0, -1, -2. A couple of values should be enough. We're graphing a line, so once we have a couple of points, we'll have an idea how the rest of the graph will look. So now we look at that inequality that's less than. We're not going to include 1. We're just going to get as close to it as possible. Open circle. And we're going to extend the graph with an arrow. It'll go to -infinity. So as it exits the graph, we're going to have an arrow indicating in what direction it's exiting the graph. Okay, let's find our order pairs that correspond to this function. So 1 in for x, 1 minus 1 is 0. 1 minus 0 is 1. 1 minus -1 is 2. 1 minus -2 is 3. Okay, moving on to y equals square root of x minus 1. Now our restriction is we're going to start at 1 and then we're going to move upwards. So we're starting at 1 and we want greater than 1, so we'll go to 2, 3, 4. Okay, closed circle at 1. And we're going to go towards 2, 3, and 4 with an arrow at the end. So let's find the corresponding order pairs, corresponding y values. So 1 in for x, 1 minus 1 is 0, square root of 0 is 0. 2 in for x, 2 minus 1 is 1, square root of 1 is still 1. 3 minus 1 is 2. Square root of 2 is around 1.4. And then 4 minus 1 is 3. Square root of 3 is around 1.7. Okay. All right, so we're going to put these two graphs onto the same plane here, quarter plane. Okay, we'll start at 1, 0, open circle there. 0, 1. Okay, so I want to make sure that we understand why we don't start at 0, right? If you start at 0 because you saw that x is less than 1, then you're missing out on this entire graph that needs to that's still part of our graph, right? We can't just get rid of this whole expression because we just want to start at the closest whole number. So we have to go all the way up to that boundary, but to ensure that we don't hit 1, we'll put an open circle there. Okay, next, y equals square root of x minus 1. We have 1, 0. And you see how there's an overlap here. So this is a closed circle. That's an open circle. If there's ever a closed circle on top of the open circle, that closed circle is gonna overtake that open circle. So this order pair is going to fill in what initially was undefined, and then we'll go to 2, 1. So I'm just doing a rough estimate here. I know kind of my general shape of my square root looks like this. So I got a line and I have a square root function. So now that we have the full graph in front of me, we're going to determine what the domain and range is. Any questions up to this point for this graph? Okay. What do you think the domain is for this combined graph here? Yeah, no breaks, right? It extends from negative infinity all the way to positive infinity. There was a potential hole here, but that hole got filled in, and so there's a smooth transition, no breaks, all real numbers. So domain, we're looking at the furthest left to the furthest right x value. For range, we want to look at the lowest to the highest y values, right? We want to start with the lowest y value that we see and move up to the highest y value. Okay, what do you think the range is? 0 to infinity. Okay. What about what do we put? Brackets or parentheses? Okay. You see how this actually does hit a y value of 0, so we need to make sure we include it as part of our range. So bracket, parentheses. Okay, questions? Okay, here's the last thing here. Absolute value functions. Okay, so we know what absolute value functions look like. They kind of have that V shape, either right side up or upside down. But typically, absolute value functions are kind of cumbersome in terms of what we want to work with it algebraically. It's just more cumbersome to work with. So the idea is if we can get it into a piecewise function, then we have expressions that are easier to work with, easier to think about. So that's a skill that we want to that we need to be able to do down the line. Okay, so think of we can always think of an absolute value function as a combination of two lines, right? You see how you can think of a V as two lines that just happen to be cut off at certain points, right? So this line extends all the way here, but we're not including this part of that line. And for this line, we're giving it a starting point or a stopping point, and we're not extending it past that point. So if we have two lines, technically we should be creating an X, but we're forcing, think of it as forcing the graph to only display a portion to get that V to show up. So basically, I also want you to see this, that there is always a positive slope version of that absolute value function. And there's also a negative slope version of that absolute value function. Another thing is there's a meeting place between the two lines. There is a place where the two lines are going to meet, and that point is called the vertex. And the way we find the vertex is we're going to be setting the portion inside the absolute value equal to 0. If we set that portion equal to 0, that will always help us find the center of our graph, the center of our absolute value function. Okay. And then once we find the center of our absolute value function, which is our vertex, that's going to be where each of the graphs will either start or end. Okay. And we're in this case we have positive square root of x, positive slope of 1x that is existing to the right of the vertex, and then we also have a negative version of that graph that is existing to the left of the vertex. Okay, so we're going to take this kind of this parent absolute value function, and we're going to build it the same way for this example 5. Okay, so the first thing we do is we need to identify where the vertex is. The vertex helps us know where our boundary is going to be. So everything inside the absolute value, we're going to set equal to 0. So we'll say 2x plus 6 equals 0. Subtract 6, divide by 2. So -3 is our vertex, is the x value of the vertex. That is going to be where the two lines are going to meet. Okay, so we're going to start building our piecewise function. We know this 2x plus 6 is going to be made up of two lines. The first line is just going to be the original expression. Just remove the absolute value away from it. So we see that this 2x plus 6, we have an idea what that 2x plus 6 is going to look like. It's going to, that's a positive slope. It's going to kind of resemble where this graph is. Okay, obviously everything is shifted, but we can tell that this the one with the positive slope is going to live to the right of the vertex. So we're going to say x is greater than -3. That just means to the right of the vertex. Okay, we also have a negative slope version of the graph. So the way we do that is we just put a negative in front, make sure we protect it with a set of parentheses. Yeah. And we want this negative slope version to live to the left of -3. So we say x is less than -3. So just a quick visual, the graph may look something like this. So the 2x plus 6 is going to start at -3 and it's going to move to the right. The negative 2x plus 6, you can tell that if you distribute that negative through, that's a negative slope. So that's going to be this part of the graph, and it's going to go from -3 to -3. It's going to be cut off at -3 to the right, so just to the left. But question, yes.
You drew a closed circle at -3, but greater than.
Oh yeah, good question. Right. So we right now, the way that I have my inequality set up, I'm not defining the vertex. So we do need to define the vertex. It doesn't matter where you put that equal sign. You can either put it with the first or the second inequality. You can just arbitrarily choose one. So as long as it's defined somewhere, thanks for catching that. We do need to make sure that the vertex is defined with, they're both hitting the same, they're both hitting the vertex, but we just want one to define it. So it doesn't matter which one. Thank you. So a lot of times we're going to be looking at the absolute value function saying, if we have to do something with it, it's a lot messier to work with this. It's a lot easier to think of it as 2-line expressions, and then we're going to have easier time manipulating it or working with it in the ways that we need to. Yes?
Wait, so when do you have to define it? Like when will you have to write the line under the?
Oh, we're always going to do it. So, but you can always choose. If I asked you to write a piecewise function, it doesn't matter. You can put it with the first one, or you can put it with the second one. Yeah, just make sure that one, because they're both reaching the same point at -3, but we don't want both defining it, so we just want one to define it. Okay, any questions here? Okay, you guys picked up the handouts? Okay, sure. Is anybody else missing this handout? So in the past years, for students coming into AP Calculus, we would have a summer packet for students to work just to kind of review pre-calculus topics. So that was required up until a few years ago, and then it became just, it wasn't mandatory anymore, just suggestions for students who want to kind of review pre-calc topics before coming into class. So I just want to, so what I did was I took that summer packet and I just pulled specific topics that I feel would be good as we are moving into our calculus topics, just to review more with the things that I think will help us out, especially on the back end with algebra skills. So one thing that's big is being able to write equations of lines. Okay. So I'm going to kind of guide us towards point slope form, and we're going to kind of work towards getting comfortable with point slope form. I think many of you are comfortable with, potentially more comfortable with slope-intercept form, which is fine, but point slope form is going to be the form that's it's going to be more efficient for our answers, and it may look a little uglier, but on the AP exam, they accept point slope form, so we can save some time by just leaving a point slope form and just moving on to the rest of the exam and not having to work on a problem that's where they're already allowing you to have full credit. So here's the thing. Anytime we want to write equation of a line, we have to gather two pieces of information. We want to identify the point and the slope. Once you identify the point and slope, we can just insert into point slope form. Okay, so number one says, write the equation of a line with the following characteristics. You may have other methods that you use where you insert it into a slope-intercept form and you solve for B, and then you work your way to solve for slope. But I want to kind of stress this method because this is going to come in. We're going to use this over and over again over the course of this year. So first thing is we want to gather the slope of this line. Okay, so the slope of this line, we want to find an equation that goes through these 2 points. So we need the slope. So to find the slope, we'll do change in y over change in x. Okay, doesn't matter which one you choose first. I'll think of this as my x2, y2, and this is my x1, y1. So here's my slope. I'll subtract the y's first. Okay, so that gives me 6/2, which is 3. Okay, so there's my slope that I can use for my point slope form. And now we got to use a point. Okay, it doesn't matter which point that we use. Both points will go through the same line. So we just pick either point. I'm just going to choose that 5,2 because maybe it's easier to work with without having to deal with a negative. So I'm going to think of this as my x1, y1. Okay, so here's my point slope form. And we're just going to insert and replace the slope and the specific point from our ordered pair. Okay, sometimes we have to go a little further and solve for y, but typically this form is acceptable. Right now, you just may feel more comfortable working it all the way down to slope-intercept form, which is fine, but just kind of giving you a preview that eventually you're going to feel more comfortable with point slope form, and you're just going to leave your answer in point slope form, even though it looks like a little messy and looks like you can still do more work with it. Yes.
And you could have put in 3, -4.
Yes, you can put 3, -4, and that'll be correct as well. Yeah, either one, they're all acceptable. Okay. Okay, so we're going to write equation of a line for all these problems. So for part B, we're writing an equation of a line that is a horizontal line with a y-intercept of -4. So I like to just sketch the graph out just to kind of see what I'm dealing with and then build the equation from there. Horizontal line that's going to go through that point. So what would be the equation of that line? Y equals -4, right? All the horizontal lines will take on the same form. So the reason why it's y equals -4 is because any point you can think of on this line has a y value of -4. So imagine we're just accumulating all the order pairs that have a y value of -4, and they're all just going to connect in a way that will create that line. Okay, try part C. What's the equation of a vertical line that passes through 7, -8? What's the equation of that line? X equals 7, right? That -8 is not going to be part of our equation. Every point on that line has the same x value, so we're accumulating all the all the x values, all order pairs that has an x value of 7. So x equals 7. Okay, part D. We want to create a line that has an x-intercept at 5 and y-intercept at -3. Maybe you have a different way of working through this, but I'm going to treat it the same method that I did with part A. I'm going to identify the order pairs, find the slope, pick one of the points, and then put it into point slope form. It doesn't matter which point I choose. I can choose 5, 0 or 0, -3. It'll come out to be the same equation. Okay, so if you ever leave your answer in slope-intercept form, that's perfectly fine. If you did your steps correctly, you will never lose points because this is a different form than what I prefer. But I am going to kind of steer you towards point slope form. Okay, questions? Okay, let's look at part E. Okay, so we want to find an equation of a line that is parallel to that given line there, and it passes through the point -6, 4. So it's the same idea, it's just a little bit more involved because we got to do a little bit more work. From this this portion of the direction here, this is where we're going to pull the slope. All we care about from that line is we just want to find out the slope. That's all we're going to gather. We don't care about anything else. So the easiest way to find the slope, yeah, I think in this case it will be getting into slope-intercept form. It's a quick way for us to pull that slope if we can get into that y equals mx plus b. So I'm going to solve for y here. Okay, I'll divide everything by 4. And get it as y equals. I can quickly pull the slope that I'm interested in. So I rearranged it to help me hold the slope a little bit easier. What's the slope of that line? Okay, negative 3/4. So that's all I care about. The slope of the line is negative 3/4. Now I want a line that is parallel to this line. So do I need to make any adjustments with that slope? Keep it right. It's gonna be parallel to it. So my slope is good. I got my slope. I got my ordered pair. Point slope form. Oh, sorry, point slope form. Okay, just try to feel comfortable leaving your answer in point slope form. Okay, questions with E. Okay, let's read F. We want a line that is perpendicular to the line 5x minus 3y equals 0, passes through the point 3478, and written in point slope form. Okay, what's different about the directions here? Perpendicular. So we're still going to go through a similar step. It's just that whatever slope we get, we're going to have to do what with it? Yeah, opposite reciprocal. Good. Okay, so let's imagine E was a perpendicular problem, right? If that was the case, then what would you do with the slope? Positive 4/3, right? And the only thing you would change is you would just change that to be 4/3, but the steps will all be the same. Okay, so try that. See if you can go through the steps for F using E as your model. Okay, from the line, get to the slope, adjust the slope, and put in the point slope form. That's already inside, isn't it? All right, good job, guys. Okay, questions? Okay. Okay, give you guys a moment to catch up if you need to look at this, but we're going to go to the back page. Okay, everybody good? So number 6, it says find the value of f of x plus h minus f of x over h for each of the following functions. What we're going to do is we're going to try to find a replacement for f of x and f of x plus h, get the numerator out of function notation so that we can combine terms and we can get it down to what an equivalent expression would be for this particular function. So an easy substitution that we can make is this f of x is easy, right? F of x is just that 3x plus 7. So we can just insert this into that portion. But the challenge is, how do we create an appropriate expression for f of x plus h? And I want to make sure that we understand how to work with that x plus h. Right now, you're looking at this, and you're not really knowing what this means. Okay? So later on, we're going to, in chapter 1 and chapter 2, we're going to see how that's related to slope, how it's related to derivative, and all that, and limits as well. But for now, I just want to make sure that we understand the back end of those problems. We want to get the algebraic portion of it down and comfortable, so that when we get to these types of problems, we can just focus on the concept, the front end of it, and then we're not struggling with the back end, cleaning up common denominators, all the algebra stuff. Okay, so what we're going to do is I have a kind of a way to kind of structure the problem so that we're knowing how to represent that f of x plus h. So this is my method of going through it. Okay. So I think the common mistake that students make is they don't know where to put that x plus h, and it kind of can be all over the place. So I feel like if I can create a structure for you guys, then you'll know exactly where that x plus h goes to build that particular function. So the way that I like to do it, or have students do it, is we're going to create boundaries for that x plus h. So what we're going to do first is, wherever you see an x, remove it, and in place of the x, put a set of parentheses. Okay. So I'm going to have us do this first. Does that make sense? You're really just removing every x you see, and then just putting open parentheses and leaving that space blank in between. Okay. If you can do this, then you're not going to make a mistake, because the x plus h is going to go inside the parentheses and only inside the parentheses. Okay, that way you're not putting the x plus h ever in the wrong slot. Okay. So here's my. So I'm just going to fill the parentheses with x plus h. Okay, does that make sense? Okay, so now that's the hard part. The students have in the past have struggling knowing where to put the x plus h, but once you can do this, then the rest is just cleaning up. Okay, we're just going to replace these function notations in with the expression. So f of x gets replaced with 3x plus 7, and then f of x plus h gets replaced with this expression, and we put it all over h. Okay, so let's do that. Now, let me ask you this. What do we have to be careful about with the f of x? Yeah, distribute the negative. So what I like to do is always protect your f of x with a set of parentheses so that you can remember to distribute the negative through. Okay, so now let's just clean this up. See if you can distribute the numerator through, get rid of the parentheses, combine like terms, and see if you can reduce it down to as simple as you can make it.
Good afternoon, Milton Eagles. Students, if you have lunch/study hall fourth period, please report to your study hall when the bell rings at 11:30. 9th and 10th graders go to lunch.